Okay, so we are going to talk today. We're starting chapter 7, and chapter 7 is basically dealing with this idea of functions of several variables. We're gonna do some really cool business applications with this, but we first have to kind of 7.1 is a pretty short section, but we first need to kind of figure out what is a function of several variables. So in your book, they say that a function of several variables, so like f of x, y, and it doesn't have to be just two variables. It could be x, y, z, or anything like that. So this is a rule that assigns, it's a rule that assigns a number to each pair. And in this case, this is a function of just two variables, but a number to each pair of values. Oh, I just messed up my pen. To each pair of values. So think about what a function is, right? A function for us, when we had f of x, we would put in one number and it would spit out another number y. Okay, so I'd put in a single number, it spits out another number y. Here's what a function of several variables does. I put in two numbers now, okay, an x and a y, and it will spit out another number, let's just call it z or something like that. So, for example, if we had, let's let f of xy equal 4x over x squared plus y squared, let's say. This is a function of several variables. As you can see, I have x's and I have y's. So what if I wanted to do some stuff with this? Let's evaluate f, at the following points. So let's look at let's just, do something simple. We'll do 1, 1, and I don't know, maybe like 0, -2, and let's get crazy. How about like 2a and b, okay? So evaluating this is kind of as simple as it looks. What would f of 1, 1 be? Well, what is x? It's 1. What is y? It's 1. So when I do this, everywhere I see an x, I'm going to put a 1, and everywhere I see a y, I'm going to put a 1. So I would have 4 times 1 all over 1 squared plus 1 squared. And so you see what we mean by what does this function of several variables do? It maps now two values, right? It maps an ordered pair to a single number. So this is 4 over 2, which is 2. So f of 1, 1 goes to 2. F of 0, -2, if I plug that in, again, I'm going to put in 0 for x. Every x I see, I'm going to put in -2 for every y I see, and I would get 0 over 4, which is also known as 0. And then the last one, f of 2a b. If I look at this one, so I'm going to put in a 2a for every x I see. So I'm going to have 2a squared, plus I'm going to put a b in for every y. So I get b squared. So on the top here, I get 8a all over 4a squared plus b squared. And that's it. That's all I can do. I know that one's a little funny. Well, I don't know. Maybe your definition of funny is different than mine. But again, please don't. None of you want to, right? Cancel this 8 and the 4. You can't do it. Don't do it. You can't do it because there's not a 4 with the b squared here. So that's just kind of a side note because a lot of my students do that, and it's an easy mistake to make. So I hope that makes sense. That's kind of what a function of several variables is. There are different ways we can use functions of several variables, well, let's, and you've probably seen stuff like this before, but, quick example, and you saw this one, in the book too, where I have like price of butter, and then I have the price of margarine. So there are different ways that we can kind of look at that. And I'll let you look at the examples in the book that are more applied. But what I want to talk about now, I don't actually want to do an example. Let's talk about the graph. Let's graph this function I want to look at this function right here, x squared plus y squared. So, you know, in the xy plane, when I normally have a regular function, just f of x in terms of one variable, we just have an x-axis and a y-axis. Well, now though, and what we used to, you know, when I had a graph of this, I would take an x value and I would map it to the y value. I would plug the x value into the function, see what is the corresponding y value. Well, now this is a little bit different, right? Because what are we actually plugging in now? We're actually plugging in an x value and a y value, and what are we getting out? Some other number z. So what a function of several variables, if it's in two variables anyway, actually does is it graphs it into 3D for us, okay? So if I look at the way we're going to look at how you graph this, and this is in your book, you know, but we look at having not only an x-axis and a y-axis now, but we actually have a z-axis as well. So what we do is we kind of put the x-axis off to the side a little bit. I'm going to put the y-axis over here so you can kind of see I've taken this plane and I've kind of just set it on its side. If you think about this, basically what I'm kind of doing is I'm making a room, and then I make my z-axis up like this. And then the x-axis continues this way. That's the negative part of the x-axis. This would be if I had a negative z, and then this would be my negative y going in the back there. So I hope you can kind of see that three-dimensionally, that this gives us a three-dimension space, which is pretty cool. So if I were to graph something like this, you can look at the pictures in your book, but a lot of ways that we are able to kind of figure out what is going on here is this idea of something called level curves. And if you've ever done any, I used to go backpacking a lot before children, and we used to use, you know, the topographical maps, right, that we would look at. Those are basically level curves. Level curves is basically taking something like a three-dimensional object and slicing it a bunch of times at different z values. So for example, if z is equal to 1, what does my function become? Remember, this is x squared then plus y squared equals 1. What if z is equal to 4? Then what does the graph look like? It looks like x squared plus y squared equals, what would I have here, 4, okay? And so on and so forth. These are what we call level curves, when we set the function equal to different values of z. And the reason we do that is because then it helps us kind of see what the graphs of these are going to be. So if I look at what these level curves show me, and then I'm going to show you a graph of this, of course. If we look at this level curve here, this is just, look at what this is saying. This is saying when I'm up 1 on the z-axis, I have a circle of radius 1. So remember, this is a circle of radius 1. So I would have at x equals 1, and up at the z-axis, I would have a circle. I'm not very good drawing 3D, so you're going to have to use your imagination. This is one of the level curves. And of course, when z is 0, I have x squared plus y squared equals 0. The only way that's going to happen is if I'm at 0. Look at what this is saying, that when z is 4, so when I'm up 4 on the z-axis, okay, I have a circle of radius 2. So I'm going to be out at 2. Remember that this is a formula for a circle, okay? So up at 4, I'm going to have a circle of radius 2. This goes behind the z-axis. And then likewise, when I'm up at 9, when z is equal to 9, way up here, I know that's not actually 9, I'm going to have a circle of radius 3. I hope that kind of makes sense. So if the idea here of level curves is what would happen if I just took a three-dimensional object, right, and I just basically started slicing it at different values of z. So what the graph of this actually ends up looking like is if we did this at all possible values. I'm really proud of my graph here, people, other than right now. My circles are really good, though. I have to say, I'm usually really bad at drawing circles. So look at what this kind of looks like. This is kind of a parabola. It's called a paraboloid. And it kind of looks like this parabolic looking, kind of, if it was hollow, like maybe a vase or a bowl looking thing. And a lot of the ways, the reason we can kind of see that that's true is because, again, this idea of slicing this three-dimensional thing for different values of z, and these are the different values of z. So a level curve is just basically taking a function of several variables and setting it equal to different values of z, so different constants, and then looking at what does the graph of those look like. So I'm going to show you guys really quick. I'm going to bringing in an online 3D grapher, and I've graphed x squared plus y squared, and as you can see, this is what the paraboloid looks like, where if we took some level curves here and slice this guy, so this just kind of gives you the shape of it. It should still be going up. This kind of just shows you what this guy looks like, right? And now I'm looking at it upside down, but that's what happens. And again, the idea of level curves, and this is your z, this is your x, this is your y. If I slice this guy, it would look like a bunch of circles. So I hope that makes sense. The last thing I want to do in this section is I want to talk about an important example of a function of several variables that is going to be important to us later on. Well, it's not that it's not important now. It's important now, but you know, we're not doing any calculus in this section. But this is a production function. Okay, and this is going to be one of the big examples we're going to use. You're going to do several examples when you do your homework, but this is the example I really want to talk about that we are going to see later on. This is the production function, and it's called the Cobb-Douglas function. Okay, so let's write it down and then we'll write what it means. Okay, so this is an example of a function of several variables. So if it's a function of two variables. Again, you can have more than one variable. So if I have f of x equals, this is the production function. I'm going to have some c. This is going to be, c is just going to be some constant. Then I have x2, we're going to say just to this a power. And then what y is going to be 1 minus a. So their exponents basically add up to be 1. Okay, so here's what this production function gives us. It's going to give us how much like a company or manufacturing company is going to produce with two kind of variables here, x and y, that are going to be factors of production. The first one, x, is going to equal our labor costs. Okay, I think that is probably pretty clear. That's just the cost of labor, right? That is what I'm going to have to spend, or that's how many, but they're going to call them units, but that's maybe how many units I'm going to spend on labor costs, right? On having workers in my plant. And then y here is what we call capital costs. This one maybe isn't quite as clear. But this is, capital costs would be, for tools. What do I have to spend for tools? What do I have to spend to rent a building or to maybe build a building to manufacture my Math Rocks t-shirts, which would be awesome. And then A and C here are constants, okay? With A being between 0 and 1, so I don't want to have negative numbers up here. But what's pretty cool about this is it tells us what our production would be at, given I'm gonna spend this many units on labor, I'm gonna spend this much on capital, right? Because if I spend too much on labor or too much on capital, one way or the other, that's going to maybe decrease my production, or vice versa. So I just want to do a quick example of this. This is a pretty interesting function, and on page 349 is the full discussion of that. So I'm not gonna go into that too much, but let's do a quick example and then we'll be done. This is a relatively short lecture for me. Consider the Cobb-Douglas equation. Okay, so here's the Cobb-Douglas equation that I want us to look at. F of x, y. And this is, where does this come from? This comes from economists that, or economists, however you want to say that. You guys are the the business people. I don't know what way you say it. So economists are usually the people that come up with, this is what we call a mathematical model, right? A mathematical model describes the way something works in mathematics or in business or whatever, and it's a way of making estimates on what's going to happen. So part A, how many, whoa, come on Sarah, you can spell sometimes. How many, okay, units of goods. So it's just units, so it's very arbitrary, right? We don't know what the unit stands for. Maybe a unit is 100 or, you know, hundreds or thousands or whatever. We're just going to say units of goods will be produced. Okay, will be produced by 81 units of labor. Again, whatever those units are. So I'm spending 81 units on labor. Units of labor. And 16 units of capital. So I'm going to spend 81 units, whatever units are, and 16 units of capital. As you can see, this should be pretty easy. You just plug it in. So this section isn't too bad. I think the hardest part probably in this section are going to be those level curves. So if you have questions on those, so raise this to the 3/4, then you need to let me know. 16 to the 1/4, and of course I'm gonna get out my calculator. I don't know where it is. There we go. You know, I could probably do this. 81 to the 4th is 3, and 16 to the 1/4 is 2. But just in case, I'm going to put this in my calculator, making sure when I put this in my calculator, when I raise that 81 to the 3/4, that 3/4 must be in parentheses if your calculator does not automatically put it in the exponent. So I get 3,240. So 3,240 units of goods. So I'll produce 3,240 Math Rocks t-shirts if I'm spending 81 units of labor and 16 units of capital. And we could, you know, we could do different things there. We could say, well, what if I spent more money on capital or more units on capital and less on labor? You could see what is going to happen to how much I will produce. Okay, I want to do, I have one more part to the same problem. Oh, yeah. You would think I would know by now. So part B, when amounts of labor and capital, last one and then we'll be done, are doubled, so is production. Show this. All right. Show this. I love stuff like this in math. Here's what this is saying. So my function, right? Let's take my function. X, y equals 60 x to the 3/4 times y to the 1/4. So let's think about what this is asking. It's saying when the amounts of labor and capital are doubled. So think about this. What does it mean to double something? It means to multiply it by 2. So when I take x and I double it, and when I take my capital and I double it, what should I show? I need to show that production is doubled. So what I need to show is that when I plug in 2x and 2y, this guy right here is going to double also, which means it gets multiplied by 2. So we just have a little bit of algebra, just algebra. I don't think I should ever say just algebra, because sometimes the hardest part of calculus is the algebra. I think you're going to like this. Look at what's going to happen here. Well, maybe not like might be too strong of a word. So I'm going to put in 2x, and for every x, I'm going to put in 2y. So look at what I've done. I've doubled my labor. I've doubled my capital, the units on labor and the units on capital. And now I just need to simplify this a little bit. So if you remember back in algebra a long time ago, I know I apply that exponent to everything. As long as it's multiplication here, I can distribute the exponent to each term. So that's what I'm going to do here, right? Because I want to get these x's by itself. So 2 to the 1/4 times y to the 1/4. Okay, I hope everyone agrees with that. I can do that as long as this is multiplication. People, if that's addition, you can't do that. So don't do it. Just step away from from distributing exponents over addition. Now I'm going to clean this up a little bit. I'm going to bring my 2 to the 1/4 over to hang out with my 2 to the 3/4 because that looks like they could be friends. And then I'm just going to leave my x and my y. And then, if you remember also from algebra, what do we do when we multiply two things with like bases? So meaning they both have the 2. Remember, what do? We add their exponents. So if I multiply these guys together, right, I'm going to add their exponents. What's 3/4 plus 1/4? That's a 1, people. That's what I wanted to see. Oh, yeah. So look at what I have here. What does this equal then? This equals 2 times 60. Now I could multiply the 2 with the 60, of course. But, you know, I just want to leave that 2 out front kind of for emphasis to be like, look at what I have. We showed, this is so cool. We showed when we double the labor, units on labor, and double the capital, what ends up happening? I double the amount of production. That's so neat. I just love that. All right, as always, let me know if you have any questions. If you get stuck on those level curves, which I know can be kind of tricky, send me a quick email. I'll write you up something to help you along. Thanks.